So we have water flows at 5 liters per second through a horizontal pipe that narrows smoothly from 10 centimeter diameter to 5 centimeter diameter. A pressure gauge in the narrow section reads 50 kilopascals. What is the reading of a pressure gauge in the wide section? All right, so rough sketch here. I have a pipe that's narrowing down. The diameter here is 10 centimeters. The diameter here is 5 centimeters. A pressure gauge. So there's some sort of gauge over here that's reading 50 kilopascals. So I'm putting P sub G to mean my gauge pressure. We want to find P sub G over here, the gauge pressure at this left side. I need to choose one of these. Ultimately, our continuity equation and Bernoulli's equations must be satisfied at any 2 points in the system. When we say they are equal to a constant, we mean they are equal at any 2 points in a pipe. So I'm going to call the wide section on the left point 1, and the narrow section on the right point 2. So when we say P plus 1/2 rho V1 squared plus rho G Y1, in the test notes, we just have this stuff equaling a constant. But ultimately, what that means is to equate all of this same stuff at a second point in the pipe. All right, so since the pipe is horizontal, there is no change in height, so we don't actually need the rho gy terms. Well, they become 0 because y1 is equal to y2. That simplifies our equation a little bit. We have P1 is going to equal P2 plus 1/2 rho V2 squared minus bringing the other kinetic energy term over. If we want, we can totally factor out the 1/2 and the rho because those are the same. And then we'll have the quantity of V2 squared minus V1 squared. And a total side note, I always see students that change that to the quantity of V2 minus V1 squared. That's not true. I know we just make silly mistakes sometimes. I do silly mistakes as well. But I wanted to point it out because that is a common mistake. Now, these pressures technically represent the pressure inside the pipe. So P1 would be the pressure within the fluid at that location 1 in the pipe. P2 would be the pressure within the fluid at the right side of our pipe. If you recall, gauge pressure, though, is the pressure inside minus atmospheric pressure. So solving this, technically P1 would be the gauge pressure at point 1 plus atmospheric pressure. Similarly, P2 would be the gauge pressure at point 2 plus atmospheric pressure. If we come down and plug that into our equation, so pressure gauge 1 plus atmospheric for P1, pressure gauge 2 plus atmospheric, and then the rest of the equation is still here. It turns out the atmospheric pressure is going to cancel. And our equation ends up looking like it did just a minute before, except that these are both gauge pressures now. So it turns out you can use gauge pressures as the p-values in Bernoulli's equation as long as both pressure 1 and pressure 2 are both gauge pressures. So in Bernoulli's equation, P1 and P2 can either both be the absolute pressure inside the fluid, or they can both be the gauge pressures measured at those points. Since we're given a gauge pressure, they tell us in this narrow section the gauge pressure is 50 kilopascals. I want to use both pressures as gauge pressures. So we know the gauge pressure too. It's water. We can look at the density on the test notes. V2 and V1, we need to know how fast this fluid is traveling at those 2 points within the pipe. Okay, coming back to the problem, they tell us the water is flowing at 5 liters per second. Liters is a volume, so we have a volume per time here. Q is that flow rate, 5 liters per second. We will want to convert to SI units. There's 1,000 liters in a cubic meter, which that conversion is, I think, page 2 of the test notes. There's a table of conversion factors. So 1, 2, 3 meters cubed per second is the flow rate. We know flow rate is not just volume per time. It can also be written as cross-sectional area times speed. So we can find these speeds. So the speed at point 1 will be this flow rate divided by the cross-sectional area at point 1. And similarly, the speed at point 2 will be the same flow rate, because it is constant, over the cross-sectional area at point 2. So our flow rate, 0.005. Area, again, they give us diameters. So area is going to be pi r squared. Area 1. Okay, so point 1, I've labeled the wider section as point 1. It has a diameter of 10 centimeters. So I will want that in meters in order to come up with meters per second on my speed. Okay, so divide by pi times 5 squared. I'm getting 0.6366 meters per second here. Make sure you keep a few digits extra when you write down your speeds. When we go to put them in Bernoulli's equation on the right, because we square them, if we round the speeds too much, it really affects rounding errors on our answer. So I always keep a few decimal places, like 4, 5, 6, somewhere around there. At point 2, we're going to take the same flow rate, divide by pi r squared. We just have a smaller radius now. The diameter is 5 centimeters, so the radius will be 2.5 centimeters, which I want in meters. So the speed here is 2.546. This will be in meters per second as well, for the same reason. Notice it's traveling quite a bit faster at point 2. And that's because the pipe has narrowed. As the pipe narrows, the speed increases. Excuse me. Okay, now that we have the speeds, we're going to solve our equation for pressure. So our gauge pressure 2, they told us is 50 kilopascals. We will want that in pascals, so I'll put 10 to the third for pascals, plus 1/2 The density of water comes off of that big table in the test notes as well. It's 1,000 kilograms per cubic centimeter. We now have our speeds, so 2.546 squared minus 0.6366 squared. I'm going to go ahead and use the digits that are in my calculator since I still have the numbers for my speeds. And then add 50. Okay. Please do not give me all of the digits your calculator tells you. Gauge pressure. We either want to write it in kilopascals, because that's what we were given the other gauge as. So we could say this is 53 kilopascals. That's beautiful right there. Because the problem doesn't specifically state kilopascals needs to be the units, we could say 5.3 times 10 to the 4th pascals. That would be totally fine as well. But please keep in mind significant figures. We cannot know these answers that significantly. So either use a prefix or scientific notation to go ahead and write that in terms of its proper SI units.